Today, our next speaker is Jacob Watkins, and he will be telling us something about improved accuracy for Trotter simulation using polynomial extrapolation.
All right, thank you, Dong. It's a pleasure to be here. So I will be talking about what Dong just said, and I will just say this is a work that I did in collaboration with Gumaro Rendon and Nathan Weeb. So just to give some context, if it wasn't clear from the previous talk, I will be talking in the context of digital Hamiltonian simulation. And this is mainly a theoretical work, so though I won't be able to go through too many of them, the work itself is in proofs. And I'll be presenting at least one of those results if I have time. The main kind of ingredients are Trotter, just simple Trotter, nothing too crazy, but with some classical post-processing in order to try to achieve more accurate results. So let me motivate this work a little bit. So Trotter formulas are very practical. They have a lot of great properties. Consider a pth order Trotter formula. You get a error scaling where epsilon is representing your error in your simulation, something like this. So for example, if you have a first or second order formula, which are very common choices, you might get, or you would get a 1 over epsilon scaling or 1 over square root of epsilon. However, a lot of the more recent algorithms, so-called post-Trotter algorithms, get you an exponentially improved accuracy, something like log 1 over epsilon, or even slightly better. And because we may expect Trotter formulas to remain quite popular, and again, they have many good properties, it would be nice to extend their reach. And it would be nice to do so without requiring too many more quantum resources to do that. So just to get you to think more about this problem, we're going to consider how we can use data collected from Trotter simulations in conjunction with classical numerical techniques to achieve higher accuracies, maybe get improvements in other ways. And so that's sort of the question we'll investigate. There have been very strong efforts in this regard, especially in recent years. So one of these methods is Richardson extrapolation. So to kind of outline this approach, consider a observable A that we're interested in computing the expectation value of. Assume that we've time evolved some system by time t. And the exact expression is on the left-hand side of this equation, but the way we compute it is through Trotter evolutions. So imagine on the right-hand side, we see these A sub j. Imagine that's the observable time evolved by a Trotter evolution in a certain number of steps, which is variable. So the key point here is we're varying the number of Trotter steps we're using across our different experiments. So we label that by A sub j, and of course that's going to be an approximation to the actual one, but it won't be exact. There'll be some algorithmic error. And it turns out through clever choice of your coefficients, A sub j, you can get even more accurate formulas. And the idea is you're sort of extrapolating to the limit of an infinite number of Trotter steps. So this has actually been done. It's been proposed, especially in the context of reducing hardware noise. So you can view it as a sort of zero noise extrapolation in that context. And in fact, there's been some recent work by folks from IBM in Switzerland who were able to show actual improvements on IBM hardware. Now, I won't be talking about Richardson extrapolation, but keep in mind the idea of varying the number of time steps and considering the functional relationship between the number of steps I take and the value that I receive for my observable of interest. So I'm going to kind of pivot on that note and just have us consider a different approach you might take. Consider the technique of polynomial interpolation. So here in this sketch, we might imagine our data points being gathered from Trotter evolutions. Maybe our data is for estimating eigenvalues through phase estimation. Maybe we're estimating expectation values. Regardless, we get some quantity from our evolution, and it's going to have some functional dependence on the step size, okay? And what we can do with that data is we can always interpolate it with a polynomial of degree 1 less than the number of data points we have. And this polynomial will go through each point exactly, so it's not a fit. And we might hope that this would be a proxy, a representation for some actual functional dependence that's existing within the system. So to elaborate on this proposal a little further, suppose we take Trotter evolutions, n of them, with different numbers of step sizes. And I'll label the step size by S sub k, so think of it as like inverse the number of Trotter steps. From those evolutions, I'm going to gather some data. This will again be through phase estimation or some other protocol. And I'll label that data by y hat. And so I'll have, in our conception, we'll have one real value data point for each of these evolutions. And these are approximations of some functional dependence, though not exact, because there'll be error in the estimation protocol. And then with these data points, I'll construct my interpolating polynomial. We'll call it, p sub n minus 1 of f. And this is an n minus 1 degree polynomial. And so just to give a sort of example of how this might look, these green points, imagine the Trotter data, we're plotting against step size. There's 8 points, so we'll have a 7th degree polynomial. Now, the way I actually generated this data was a noisy perturbation of just a cosine squared function. I just chose that sort of as an example. We don't know what that's going to look like. But you can at least see in this example, thankfully, we have some close-ish relationship between the underlying cosine squared distribution and the polynomial fit we see, at least within the data points. And whether or not this convinces you it will always work, maybe it really shouldn't. But that's sort of the purpose of this work. Now, you don't necessarily want to do interpolation with any set of nodes if you're familiar with this problem. In fact, that naive choice of a uniform set of nodes has some poor numerical properties. It's not very well conditioned. But there are a good choice of nodes, and actually good for several different reasons. The Chebyshev nodes, which you can conceive of as the projection onto the x-axis of uniformly spaced points on the circle, or if you like, the zeros of Chebyshev polynomials. These are an excellent choice of interpolation nodes for both numerical reasons, and also for the fact that they tend to anti-cluster around the origin. I mentioned that we're plotting against step size, so think about going towards the origin as being more expensive, right? We're taking smaller Trotter steps. If you're curious, I'll also just briefly mention, you can define a negative step size in a reasonable way, which you can ask us about later, but it's not too crazy. So we're imagining getting the data at these particular choices of Trotter step size. And in our work, we're considering, in particular, the class of Suzuki Trotter formulas of even order. So in this case, they're order 2k, where k is a positive integer. So for example, k equals 1 is a symmetric formula. So we are sort of interpolating this, attempting to sort of approximate this underlying function f of s, which may be the relationship between a phase estimation protocol and the number of steps you chose. And in our work, we consider eigenvalues and time-involved expectation values in particular, but perhaps there are other applications as well. And s equals 0, corresponding to sort of an infinitesimal step size or an infinite number of Trotter steps, is the ideal perfect evolution that can never be reached directly on with the Trotter simulation. So I guess the idea is we would like to not go so close to the origin, but maybe take some surrounding points and see if we can learn about the behavior at that point to some accuracy. So we're sort of trying to mitigate the algorithmic errors rather than sort of mitigating a hardware error. So there's sort of a connection here perhaps to these sort of zero noise extrapolation techniques. Okay, so let me just give you a picture of some of what I just said. So here on the x-axis, we're plotting the step size, and I invite you to consider maybe an expectation value problem where the operator of interest is O, and we have a simulation time t, which is fixed, but we are varying the step size s. We have some underlying functional form, which we don't know about, but we gather, oh, and I'll also say, we need to make a choice of the width of our interpolation interval, and this is going to depend on sort of the simulation time, the size of the Hamiltonian. We need our points to be accurate enough to the true value in order to get a good interpolation. Then we gather our data. Those points are the quantum computational part, okay? So we might be doing some phase estimation or something. And they're distributed somehow around f. We fit it with a polynomial. And at this point, we hope, and with some numerical or some theoretical work, we can try to understand this. We hope that at the origin, s equals 0, our polynomial is a good approximate to f of 0, which is the exact value. So in our work, we consider several different approaches. They're kind of broadly classified as either eigenvalue or phase estimation applications, and also expectation values. And for the sake of time, I will just tell you the results of the expectation value analysis. And in the questions, you can ask me about the some of the details in the proof if you're interested. So I'm about to display the main results, but on the right here, I just listed some notation for your reference. What I'll be showing, which is sort of maybe a segment of our result, but maybe the main part, is sort of the quantum cost, which we identified as the number of Suzuki-Trotter exponentials that we need to take. This is sort of going to be a proxy for the quantum part of our cost. And we have a fixed order Trotter formula, et cetera, et cetera. So the main result is that we can compute time-evolved expectation values using Trotter, amplitude estimation for the protocol, and our interpolation, with the cost scaling like this sort of messy formula. So key things to focus on here. C is essentially proportional to the simulation time. We have, right in the middle of that nx formula, a C over epsilon. So we have something, a term proportional to t. And we also have this interesting max C log 1 over epsilon term, which I will talk about in the next slide. So I'll keep the results. And some key things we get from this analysis, we're able to obtain sort of what I'd call maybe a near-term, or a near Heisenberg scaling. What I mean by that is we get a 1 over epsilon in the estimation protocol, but we still get some logarithmic factors that show up. One really kind of odd thing about our approach is that we're not only learning s equals 0, we're learning sort of something about the entire function for the interval that we're interested in. This is sort of a uniform approximate, unlike extrapolation techniques. So whether that's useful or not, I'm not so sure yet, but it's kind of interesting. The scaling, and I find this to be an artifact perhaps of my analysis, is either linear or quadratic, depending on how severe your error requirements are. I believe this comes from some weird dependencies on the simulation time versus the number of points, but you can ask me about that if I have time. And I guess I'll finish by suggesting that maybe this is something that we can try in the near term, because really we're talking about doing Trotter simulations and doing some relatively minor classical processing. So maybe this is something that would help us mitigate algorithmic errors. So thank you very much. We have an archive. Feel free to look at this. And I'm happy to answer any questions.
Yeah, thanks, Jacob. Yeah, we have some time for a few questions.
Yes, this is nice. So I'm curious, do you make any assumption on so I'm just surprised that you can get some rigorous proof about the accuracy. Do you make any assumption about the Trotter?
Yeah, so I have some extra slides because I didn't talk much about the theory at all, so now that you've asked. We do make some assumptions on the functional form. We don't actually maybe make the strongest assumption possible, but we consider our f to be smooth. This is a reasonable, if you look at sort of the dependence on the Suzuki-Trotter formula in terms of this parameter s, you do see smoothness. And it turns out there's some well-established results in polynomial interpolation that let you write the error within your interval as some sort of generalized, what would you call it, like Taylor remainder. And you can find this in a textbook. You can also find this equation in our paper as well. Does this answer your question? Great.
So if you're looking at an observable at time t, then a valid step size would be like a t over s is an integer, right? But here you're choosing Chebyshev nodes. Right?
Yeah, you asked a great question. And if I had 5 extra minutes in my talk, I would have talked about this very precise point. The question is, so we sort of treated s as this real value quantity, but in fact, if s is 1 over an integer, how do we make that compatible with sort of an arbitrary choice or with a Chebyshev interpolation point? There are several answers to this. One of them is NIST and one of them isn't. I'll start with the non-NIST one. You can always do fractional queries using QSVT with a constant overhead and no changes sort of to the time scaling. There also exists, so the other thing you could do is perturb your Chebyshev nodes to the nearest reciprocal integer, thereby doing an integer step. This gets more accurate as you take your interpolation interval closer and closer to the origin. There are mathematical results that show that your well-conditioning of your Chebyshev interpolation does not change too much if you perturb a little bit, so there's sort of robustness. Unfortunately, my analysis currently would lead to slightly worse scaling than I showed you here. So because of this sort of quirk where I have the number of interpolation points growing linearly with the simulation time, which I strongly believe can be improved. So I chose to kind of take the loss, if you will, and say, we'll do fractional queries, we'll have O1 overhead. Now, I strongly believe if you were to implement these and you just did integer, close approximating the Chebyshev, I think it would probably be okay, but my theory doesn't really support that yet.
Thank you.
Okay, great. Yeah, thanks, Jacob again.